Hey, this is Dave with OC Astronomy, and we're going to go through some more Openstax Astronomy. Today we're going to look at Chapter 2. And so today's chapter is introducing us to the idea of how the heavens appear to move around us, and also what the ancient astronomers thought about this whole system of the Earth and the stars and how things looked. So let's dive right into it. If you enjoy the videos, please give it a like. If you're one of my students, I'd appreciate you giving me some feedback on how this is helping you, or if it's helping you. If you're just some random nice person on the internet, hey, thanks for watching my channel. All right, so Chapter 2 starts out talking about the zenith and the horizon as our natural observing point of view. So the zenith, technically, the zenith is wherever you are on the Earth. It's the thing, the star or whatever that's right directly above you. So let's find Oklahoma. Here's Oklahoma, yay, right there. And so right above Oklahoma would be the stars at its zenith. And then the horizon would be any stars or the sun or whatever else that we can see going off on the level ground point of view. And so if you were to move, let's say that we were to be down here, where's this? Puebla, Mexico, and you were in Puebla, Mexico, and you looked at the zenith, and then you were compare that to Oklahoma's zenith, the star that's at your zenith will change. We don't say this is at the zenith, and then we go to Puebla and say, oh, our zenith is over here. No, the zenith is always directly overhead, and your horizon is always what's level to the ground out in any direction around you. And so this gives us a little bit of a problem because when you're talking about the location of a star in the sky, how can you say exactly where it is? Because if you're in Oklahoma and you say, well, right now that star is directly over me, well, someone in Puebla, Mexico would say, no, it's not. It's shifted over here. And it's going to shift by the amount of your latitude away from the equator. And so zenith and horizon are useful, but they're very difficult to use for describing the location of stars. We have the celestial poles, and I'll use the star globe as an example, but we have stars that are towards the north and stars that are towards the south, and everything else rotates around every day, or actually, the Earth, imagine the Earth being a tiny ball inside this globe, and it's the Earth that's actually spinning, and it makes the sky to appear to rotate from east to west. And those, we have the poles, the North Pole and the South Pole, and then we have the equator. And so we like to use celestial coordinates to point to the poles and the equator because that gives you a system that's more like longitude and latitude that will give you a true pointing at those stars. And we actually have the celestial poles and the celestial equator, which is just a projection of those points on Earth out into the stars, and that's how we can map our way around. So if you're on this globe and you're at the equator, then it is possible with the help of a little bit of elevation, maybe from a mountaintop, and then also with some of the effects of the Earth's diffraction, it's possible but very difficult to see both polar regions at the same time. The exact North Pole star out here and the exact Southern Pole's stars out here. There's not one particularly strong Southern Pole star, but you could see the groups of them that are there. And you could see them from the equator whenever you look one way or the other. And what you would see is you would see the polar stars rotating around the edge of the horizon until it got to the end, and you'd see some of those stars would barely come above the horizon and then quickly set. Meanwhile, the stars that are coming directly over you would pass directly overhead, and then those stars would set directly from the east into the west. And then the same with the southern stars, you could see them rise briefly and set really quickly if you're at the equators. If you're at the northern pole, however, those same stars that would appear to rise and set really quickly, if you're at the equator, the ones that if you're at the pole, that star would never set. It would always be at your zenith, and then all the other stars would appear to rotate around your horizon at a 90-degree angle. And so you would see a panel of those stars rotating around and it would always be rotating like so, and you would always be seeing the stars that are above the horizon to your zenith to the other horizon, and they would never change from the north. And then flip it around, same thing at the southern stars. As the Earth was rotating around, you'd see the stars at the southern pole, and then you would see basically a panel of stars around that would be a true dome overhead, and they would never appear to set on the horizon. For any of the rest of us, unless you're at the equator or at the poles, what you see is a kind of a combination of both. So if you're in the northern hemisphere, you can look up at the northern pole stars, and those stars will appear. Some of them will appear to rise and set really around the pole, but there is a region, the circumpolar region, where there are a group of stars. If you go small enough, there's a small enough circle from pretty much anywhere that you are north of the equator, that those northern stars will never set. They will always be above the horizon, and you can always see them tracing out a circle. And then the closer that you get to the North Pole, the bigger that circle will be, until directly overhead is the entire circle, and they would never set. And then the same thing going to the south. So that's kind of our perspective on the stars that are directly above our heads. Now, there are also a special set of stars that pass around the center. We call those the Zodiac. We got Leo, we got Cancer, we got Gemini, we got Taurus, etc. Those special ones that you've probably heard of as your star signs, those are special zodiac constellations. Those are the locations of the sun during the year. And as the sun passes on a path that's not equal to the equator, it passes on a path that takes it from a southern zone to a northern zone and back to a southern zone. The Tropic of Cancer through the equator, through the Tropic of Capricorn, back to the equator, to the Tropic of Cancer. And the sun appears to shift through that cycle, and it does it through these 12 constellations. Now, I hate to break it to you, there's actually 13 constellations in the zodiac. One of them is called Ophiuchus, but you've never heard of Ophiuchus, have you? That's because astrology hasn't really kept up with science or even really kept up with its own constellations. The sun moves through the constellation Scorpio for just like 11 days and actually spends another 20 or so through the constellation Ophiuchus. And so I don't know any of you that might have a birth date that gives your star sign as Ophiuchus. Now, your star sign is where the sun would have been when you were born. And so this is an important thing about the zodiac. The zodiac is where the sun is located. And so during the month of, let's say, Sagittarius, when the sun is in Sagittarius, you can't see Sagittarius because the sun is shining and it's blocking out and it's in the way. So you can't see the star sign that you're associated with because that's where the sun is and it's too bright and you can't see that constellation in the background. We'll get to astrology in a little bit. It's fun to talk about, but it's just, one of those things that you kind of need to know for pop culture, but it does not at all affect your everyday life. All right, so in addition to those stars, those special stars, the constellations, the zodiac signs, and the northern and southern circumpolar regions, you also have some stars that we might call the wandering stars. And those stars are stars that appear to move against the background of the fixed stars. Planets comes from wanderers, and that means the stars that wander, and they appear to move. Now, one of the things that really flummoxed the early astronomers was these moving stars and what to do with them in their world system. And so a lot of times to the ancients, they made those their gods, and they said that those gods were in the sky, moving around, doing godly type of things. And so that had a profound effect on things. But we now know those to be planets, and that those are actually bodies orbiting the sun just like us. We'll get there in a second. So what did the ancient people think about the world that we live in, the stars that are overhead? A lot of times we give credit to the early Greeks, and a big reason for that is that we have some of their stuff written down, or if not their exact writings that they themselves wrote, we have them being quoted by other people in other documents that survived, and so we know what they were saying even if we don't have their original writings. And one example of this is Aristarchus of Samos. This is a neat little book, Aristarchus of Samos, the Ancient Copernicus. Why do they call him the Ancient Copernicus? Because Aristarchus was able to reason that the earth was round and that the earth moved around the sun. And one of the things that he observed, or that the ancient Greeks had observed, was that the earth was round. They came to that conclusion, well, for several reasons, but they saw the shadow of the earth on the moon during an eclipse, and you could trace out, and it was different than the shadow that you see during the moon's phases. The moon's phases come because of the angle of the sunlight hitting the moon, but the shadow that's cast on the moon during an eclipse comes from the actual shape of the earth as its shadow hits the moon. And so they were able to look at that shadow and reason out that the earth must also be round, just like the moon was round. So that was one reason for it. Aristarchus was an interesting guy. He came up with this idea that the earth was the thing that was moving and it was going around the sun, but he didn't have as good of a publicist. His competition was Aristotle, and you've probably heard of Aristotle if you haven't heard of Aristarchus of Samos. Now, why have you heard of Aristotle? He was a very famous philosopher. We have, again, quotations of his work that appear in other people's works, and so we know about him. And along with his philosophy and reasoning, we also have some of the reasoning that he did about the sun and earth system, and that the earth was the thing that was fixed and the sun was the thing that was moving. One thing that bothered the ancient Greeks about the earth moving was something called parallax. And there's actually this book here, the Parallax, the Race to Measure the Cosmos. Very, very good book. By Alan Hirschfeld. Parallax is when you have an object that's in line with another object and you move, then you can see the shift because your angle changes on how you're seeing things. So if I hold my finger up here, line it up with the camera, and then I move, then my finger appears to move. And if I move over this way or this way, I'm not moving my finger, just moving my head. And so I appear to move, my eyeball appears to move against a fixed point reference. So one thing they said was, well, if the earth is moving around the sun, then the background stars should also appear to move. And that's good reasoning, but the only reason why it was flawed was that the background stars were so far away. They were impossibly far away for them to even comprehend at the time, given on how big the earth was, how far they must be. Aristarchus, I think, reasoned that, and his reasoning was they must be therefore impossibly far away. But again, he didn't have Twitter, and Aristotle did, and so his message got out, and Aristarchus' message got squashed, and Aristotle ruled the day. So the idea of parallax will come back after a while, but for the ancient Greeks, they said, well, since we're not seeing this shift as the earth is going around the sun, then it must be that the earth is not moving. And so that was one argument against it. In fact, it took into the, I think, 1600s before we actually measured parallax. So the earth, therefore, they said, was not moving. But they did say that it was round. A guy named Eratosthenes figured that the earth was round, and that if it was round, we should therefore be able to measure it. He heard about a well in the city of Syene in Egypt. And apparently in this well, on one day a year, the sun overhead shined down into this well, and there was no shadow cast at the bottom of the well. Now, Eratosthenes, being the smart guy that he was, reasoned that therefore the sun must be directly overhead in the city of Syene to hit the bottom of this well without casting a shadow. Because if the sun were any way to one way or the other around this well, it would cast a shadow and you could see it, but only if it was directly overhead. And then he knew, well, on the day, it happens one day a year, so on the day that this happens in Syene, I know that in Alexandria, we get shadows. We get shadows. Things are not directly overhead. And so he reasoned that therefore, if the sun is directly overhead of that well, and then you have Alexandria, where the sun is not directly overhead and it's casting a shadow, that you could actually make a triangle between the sun, the well, and Alexandria, and using similar triangles and the shape of the shadow that was cast, he used geometry and the ratio of similar triangles to make a pretty good guess of the size of the earth. I think he reasoned it was from Syene to Alexandria was 1/50th of an angle, and so he reasoned that it was 1/50th of the arc, and so the total distance around the world must be 50 times that from Alexandria to Syene, something along those lines. But he just used reasoning, similar triangles, geometry, and actually a really good insight about the sun having to be directly overhead to say, hey, let's put a distance around the earth. And they actually got pretty close. Then there was also Hipparchus. Hipparchus is another famous Greek astronomer. He was famous for coming up with the early system of celestial coordinates and of projecting this idea of there being an equator, a celestial equator, and celestial poles, and using that as a reference grid to map out the stars. And he mapped out a large portion of the stars and made some star maps with great precision. And one great thing that Hipparchus did was he came up with a system of apparent magnitudes. And apparent magnitudes were how apparently bright is a star. And this is how he kind of did it. If you go out right as the sun is setting and you look in the sky for when the first stars start to appear, you can see a smattering of those stars. There's only a handful of them, maybe 60. And you see those really brightest stars, and those are the stars that appear first. Now, after some time, and the sun goes down a little bit, and your eyes are getting adjusted, then you can see a second group of stars, a second group of bright stars. And those would be the stars that you see second. And after a while, the sun sets, and you see some more stars come out, and there's a lot more of them now. They're starting to build up in number, but those are the stars that you see third. And so you can see his order was the stars you see first, the stars you see second, the stars you see third. And it actually flips what you would think would be the brightness value. You would think that the brighter the star, the higher the value would be, but we have it flipped the other way, like golf. The brighter the star, the more likely you are to see it first, and so its number is 1, and then second, and then third, and then so on. And so your magnitudes actually increase for dimmer stars. But good for Hipparchus for being that guy that found that out. Another thing Hipparchus did, besides celestial coordinates, besides magnitudes, this dude was on fire. He also compared notes between his observations in the celestial coordinates and the observations that he had access to of the ancient Babylonians, to him, they'd just be the Babylonians. The stars that they said never moved, the stars that were circumpolar and always moved around in a circle, were different stars than the stars that he noted. He came to the conclusion that these stars must therefore have moved over these hundreds of years. And so we have something called precession that he noted, and the stars actually do shift slowly. And the reason is the earth has a slight wobble to it, so the stars that are directly overhead over the north actually wobble a little bit. And we call this precession. Back in the day, the northern pole was not at a star called Polaris. It was at a star that we call Thuban, and Thuban was the pole star for a while. Then there was a star called Kokab, which I think is Hebrew for the star. And I think that Kokab was the North Star for a while. And now we call it Polaris as the North Star. And it's the star that appears to be the North Star. And it's precession that's causing this to move and to shift. So the early Greeks were onto a lot of it. And one of the reasons why we give them a lot of credit is we have a lot of their ancient writings and we have access to them. There may have been other ancient astronomers that were on point and had all this down and even had a system of it, but we don't know about them because we don't have their writings or people talking about their writings that survived. It's not to give just credit to the Greeks, but hey, credit to the Greeks, they wrote some stuff down. One of the guys that wrote the most down, or wrote the most important book down, was a guy named Ptolemy, and I'll call him Ptolemy in case you're looking him up. Ptolemy. Ptolemy. So Ptolemy wrote something down, and he wrote down everything that he had access to in the Library of Alexandria. And the Library of Alexandria was a center of culture and learning, and it was a great thing. And you might call Ptolemy the chief librarian of the Library of Alexandria. And one of the things that he did was he compiled some of the important knowledge that they felt was most important, and some of this was about astronomy. And he compiled it into this book about natural history and the earth and everything they knew about it. But his system of astronomy that he wrote down was the Greek system of astronomy that they had the best records of and everything. You might consider him as like the Wikipedia of his time. He may not have made the discoveries, but he was the guy that wrote them down and condensed them into a form. And he also wrote down the mathematics that he could. So it wasn't just statements of fact. It was statements of fact backed up with the best Greek trigonometry that money could buy at the time. His math was very, very good. And the system that he used was that the planets moved around the Earth in circles, and they called the main circle that they moved a deferent. And something that they had to do to square things with their observations was they couldn't make it work if you made the circle go around the Earth. So you have a point in space that was the Earth and an equant, and then you had the center was opposite or in the middle between the Earth and its equant. And you had this center point became the center for the circle. And if you shifted that circle to the center point between the Earth and the equant, then the system will work. If it's centered at the exact center of the Earth, it doesn't work. But they reasoned that for some reason, the center of these circles that they're looking at is just off from the center of the Earth for whatever reason. So they go around the Earth, they just don't go around the exact center of the Earth. They're off by a little bit. The other thing that he had to do was explain retrograde motion. Now, retrograde motion is interesting. If you are on Earth and you're looking at Venus or you're looking at Mercury, then you won't see it. But if you're looking at the stars, the planets on the other side, if you look towards Mars and Jupiter and some of the brighter stars, planets, then you'll see that those planets will go backwards. They'll appear to go backwards. The reason is that as the Earth is going around during the course of the year, Mars is out here doing its thing going around, but Earth moves faster than Mars. And so from a point of view here to a point of view here, Mars is going to trace out a short arc, and the Earth will trace out a large arc. And from one side of this arc to the other, the Earth will go faster than Mars will go on its little piece of the arc out here. Now, what that causes us to see is we see Mars move across the sky, and then as we go around and speed past it, we see Mars appear to go backwards. And then after a while, it shifts again and goes forwards again. And this motion is called retrograde motion. And if you've ever heard anything crazy on the news about Venus being in retrograde or Mars being in retrograde, that's what you'll hear. Jupiter's in retrograde. Oh my gosh, we're all going to die. But retrograde just means that you see the path of the planet going backwards for a short period of time. Now, the real reason for that is, like I explained, the motions of the Earth and Mars, or Jupiter or those other planets. And so Ptolemy's system had to explain that. So we had the deferent, which is the main circle that the Earth moves on. And they had to add something called an epicycle, which is a little circle, and that's what they said the planet moves on this little epicycle. And as it goes around the deferent, it moves on its epicycle around and around. So as we're seeing the planet go around us, it's actually moving on a little circle slowly over the course of several days or weeks. We're going to see Mars appearing to move backwards because it's going around on its epicycle as it travels on its deferent. Now, to us, that may not work. You know, they had to have these circles off-center. They had to have the epicycles, and it sounds complicated, and it is complicated. and trying to read through it brought me to many nights of good sleep. But in Ptolemy's day, that was the best system they had going. In fact, later on, some Islamic raiders came through and attacked Alexandria. Some Arab raiders came through and attacked the city. And they actually gutted the city and burned the Library of Alexandria. But they were able to save some of the most important books out of it when they realized what was going on and that this was a big library. They were able to pull some of these books out. And one of the books that they grabbed was Ptolemy's set on the natural sciences. And his books about astronomy, especially, they highly prized. Because in their journeys through the desert, they also used the stars as a guide. So knowing how to find your position with the stars and knowing how to find the planets' positions and so on was like gold to them. In fact, they titled this book the best book, the Almagest. This book is the best. It's the best. And so the Almagest is the best book. And Ptolemy wrote it, but he also assembled it from the best knowledge that they had at the time. So this book was primo. It was number one. It was the best, the Almagest. So that system survived for a long time, and the reason why it survived was that Ptolemy's math model for what was going on was accurate. It was accurate in making predictions. And Ptolemy's predictions were, where are these planets going to be? And to the astronomers, or the astrologers back then, the predictions of where those planets were going to be was everything. They were the wandering stars. It was easy enough to tell you where any of the stars were going to be, except those wanderers. They needed to nail down their positions. And Ptolemy's model worked to put those positions in the right places, or they worked pretty well. Along came a guy called Copernicus. And so he got to looking at things and he said, things would be a lot simpler if the earth moved. And let's make the earth move, and I'm going to just work out the math and see what happens. So he spent many years of his life writing a book called, and I'll probably mess this up, but De Revolutionibus. De Revolutionibus. There was one flaw with De Revolutionibus. The model that Copernicus used, he was still kind of stuck on the idea from the Greeks of perfect circles. And he had this idea that we need to make the orbits perfect and circular. And so he put the earth moving around the sun, and he put the sun where it needs to be, and all the other things doing what they need to do, and the moon going around the earth. But he made all the orbits perfectly circular. Now, something interesting happened. Because we've figured out that they're not perfect, they're actually slightly elliptical. We'll get to that next chapter or so. They're slightly elliptical, and the problem with that is it made his system of perfect circles slightly off on its predictive power for predicting the locations of the planets from our point of view. In fact, it brought down the quality of his prediction because he insisted on circles being perfect, and it brought down the quality of his predictions to where they were just about as good as Ptolemy. And Ptolemy, you got to remember, wrote this book that everyone called the best, and they called it the best for 1,500 years. So 1,500 years worth of being the best book versus a new guy on the scene and his book. So you could kind of see where the people of the day said, well, let's go with old knowledge that we know to be true versus this upstart youngin, Copernicus. We're going to go with what we know. Now, it's kind of a shame because it took a while for that to catch traction, but thanks to Kepler later on and modifying it slightly to where we have elliptical orbits instead of circular orbits, then now we know the system works. And one of the key guys that was responsible for that was another great scientist named Galileo Galilei. Maybe you've heard of him. Galileo Galilei was actually kind of a math tutor. He was the personal court mathematician for the Grand Duke of Tuscany. And he really was studying ballistics and motion, and he wasn't at first really an astronomer. But he was studying the motion of objects as they roll, as they slide, as you drop them, and so on. And so he had an idea about motion, and that's one of the things he was looking at. And so he was a man of lots of talents, and one of the things he did read about astronomy. And he saw Copernicus's book. Actually, he became pen pals to a degree with Kepler. And Kepler wrote him saying, Galileo, I really wish you would take a look at this book, Copernicus, and I wish that you would come out and formally support it. Now, Galileo kind of was hemming and hawing a little bit about that because, there were still people hanging on to Ptolemy, and those people actually were pretty important people. Some of them were even his bosses and people in the church and the Pope, for instance. And he didn't want to upset the apple cart by necessarily calling them dumb. So what he did was he wrote a book and he called them dumb. What happened was he wrote a book, Conversations About World Systems, and he made the two characters, one of them, the sympathetic character or the hero, was the person who said that the earth is in motion around the sun. And then the person who is not the villain, but the kind of the dummy doing the arguing, he made this person the person that said that the earth is still and the sun is moving around it. And kind of he got in a little bit of trouble because the way that he described the dumb person, he actually was describing a guy that looked a lot like the Pope. Not a way to make friends, especially when the Pope got a hold of it. But anyway, that's a whole other story and political stuff. But one of the things that Galileo was most famous for was he's the first person to take a telescope, or actually a spyglass, and they had gotten the spyglass from the Dutch, and they had been using it to monitor troop movements, to monitor ship movements into harbor. The spyglass was a very useful invention. But Galileo, being the curious guy that he was, actually took the spyglass and looked at the moon. And he looked at some other bright things in the sky. And he saw that the moon's surface was not perfect. It wasn't a perfect sphere like we thought. For a long time, they thought that the different shadows on the moon's surface was because the light was reflecting off of the earth, and it was the imperfections of the earth that were being reflected up into the moon. And instead, it was actually that the moon had craters. And he saw those craters in the mountains on the moon through his telescope. He also looked and saw the planet Jupiter, and he saw that there were some bright bodies, 4 moons, that he tracked over the courses of many nights, and he saw pretty clearly that those 4 bodies were going around Jupiter. And that caused a real problem, because Jupiter was said to be moving through space in its crystalline sphere and doing its thing on its epicycle and on its deferent, and nothing else was supposed to be going on. And now it turns out that there's 4 other bodies that are rotating around it. And then he also looked and saw the phases of Venus, and he could see from the different phases of Venus that they matched up with Copernicus's idea, and the way that the phases happen on Venus can only happen if Venus is coming in between the Earth and going behind the sun. That's the only way that you can get the pattern of phases that you see on Venus. And so between all those different lines of evidence, Galileo really had to say, look, Earth is moving. When Galileo turned his telescope to the sky and saw the proof that Copernicus's system worked and that the heliocentric model was right, and then Kepler came along and added in that the orbits were elliptical and not perfectly circular, and you had a better mathematical system that made better predictions, then that system really brought the Ptolemaic system crashing down, and after a while, that became the dominant system. But that really marked the big change between the ancient astronomers and all the ancient knowledge that we had and what we consider to be kind of modern astronomy. And it was the birth of the telescope and using the telescope to look and see what's in the heavens and examine things a little bit closer. That's what got us to where we are today and to what we know about the world and to what we know about the system of how the stars move around the Earth and the Earth moves around the Sun, and the Sun and the Earth system move through the Milky Way and where we are today. That's chapter 2. I hope you've enjoyed it. I hope that it gives you enough of the answers for your quiz material. And until later, this is Dave with OC Astronomy, and enjoy some clear skies out there.